Last week, we learned how to use the Hero Junior's RS-232 machine language monitor, and we re-entered the Hello World program from episode 4. We also modified Hello World to work when running from the monitor by writing a new routine, announce, that waits for the voice to finish before returning. This week, let's keep the ball rolling and look at the Junior's other major form of communication, its keypad LEDs. We've seen the set of 8 red LEDs blinking wildly every time the robot speaks, but they're not just a blink and light display. They can be harnessed for our own purposes as well. The LEDs are driven by U215, PIA number 2, and by writing values to the PIA registers, we can output binary patterns to the display. Let's borrow a ROM routine to help us out. It doesn't have a real name in the official ROM disassembly, but I call it LED out. It lives at address EC3C. To use it, we load a number into the A accumulator and then JSR to the LED out routine at EC3C. Let's give it a try with hexadecimal 00. Here's the routine written out. We've seen the JSR and RTS instructions before. They just jump to the LED out routine in ROM, and when it's done, the RTS returns us to the monitor. Or rather, we'll trigger the monitor to return to itself before it executes the RTS. Recall that the 6808 microprocessor has 2 accumulators named A and B. They are 8-bit wide specialty registers that are used to store the results of arithmetic operations. CLR-A is a new instruction which simply clears the A accumulator. It just sets it to 0, plain and simple. Let's load this short routine into memory at address 0830 and run it from the monitor. If you need a refresher on using the monitor, see the last video, part 6. Before we run the routine, let's take a look at the lights in the robot. They're in a pattern that they seem to end up in often. Let's note it down for future reference. And now we run our routine to turn them off. And they turn off. Mission accomplished. Let's get fancier. Suppose we want to display something interesting on the LEDs. First, we would load an LED bit pattern into the A accumulator, and then JSR to the LED out routine at EC3C. Let's give it a try. But first, I need to explain what I mean by LED bit pattern. The 8 LEDs on the Junior's keypad represent the 8 bits of a binary number. So let's imagine a pattern of 8 LEDs with 1s for lit LEDs and 0s for unlit ones. How about this pattern? That's the value that we need to load into the A accumulator before we call LED out. The only problem is, it's a binary value and we need a hexadecimal one. I'm including a link to an Addendum video where I go over binary and hexadecimal numbers in detail, but here's the very short version. Any 8-bit binary number can be broken up into 2 4-bit binary numbers, so 11110000 becomes 1111 and 0000. And each of those 2 smaller numbers, which are called nibbles by the way because they're tiny bytes, can be replaced with the equivalent hexadecimal digit from 0 to F. So 1111 becomes F and 0000 becomes 0. Here's the code. So we load the A accumulator with hexadecimal F0 and then JSR to LED out at EC3C. We'll put this short routine in memory at 0835. Now we set the program counter with Control P and call the Go command with G083A, which is the address of the new routine's RTS command. This lets us get back to the RS-232 monitor when the short routine is finished. Now we can see the relationship between our 8-bit binary pattern and the lights on the display. The pattern reads correctly if we look at the robot from its left side with its right side as up. We see 4 LEDs on and 4 LEDs off, matching the binary pattern we sent. In fact, if you notice the markings on the LED display, you'll see the numbers 0 to 7. These mark the actual bit numbers of the 8 bits in a byte. Again, looking from the robot's left, we have bit 0 on the far right and bit 7 on the far left. Again, if you'd like a deeper dive into binary and hexadecimal numbers, have a look at the addendum to this video linked above. Okay, let's say we'd like to display more than one pattern, perhaps alternating between 2 different patterns to make a simple animated display. We can't just load the first pattern, display it, load the second pattern, and display it. I mean, we could, and you're welcome to give it a try as an exercise, but you'll end up seeing just the second pattern on the display. Remember, the 6808 microprocessor in the Hero Junior executes 1 million instructions per second. So it does indeed load and display our first pattern, but then it replaces it with the second pattern before we're even aware the first one was there. It happens in microseconds. So what we need is a routine that we can call between the first and second patterns to slow things down. We need a delay routine. How about one that waits for a specific number of milliseconds? If we use the X register to hold the number of milliseconds we want to delay, then we can wait up to 65,535 milliseconds, or just over 65 seconds. That sounds about right as a maximum wait time. If we need something longer, we can always call it twice. Here's the listing. It's surprisingly short. I've decided to use accumulator B here as it gets less traffic. It's more likely that accumulator A will have some important number in it when you happen to call the delay routine, so using B saves us from having to save then restore A somewhere safe. Let's look at the delay routine line by line. The first line loads an immediate value into the B accumulator. I arrived at this value of hex 75 by fine-tuning my original choice downward to get as close to 5 seconds when calling the routine with the number 5000 decimal. 5,000 milliseconds equals 5 seconds. Basically, we're setting up a loop to waste time, exactly 1 millisecond of time, hopefully. Next is the NOP instruction. Same as in our last video, it's here to waste more time. NOP throws away 2 processor cycles each time through the loop. Now we decrement the B accumulator, taking away 1 from it each time through the loop. Eventually, we arrive at 0, which brings us to the BNE instruction, branch if not equal to 0. It checks to see if the last action resulted in a 0, so it's checking on the value of the B accumulator each time around the loop. Until we get to 0, the BNE instruction sends us back to the NOP instruction to waste more time and decrement B again. So we do that first small loop, hex 75 times, and then execution continues with the DEX instruction. Recall that we jumped to this whole delay subroutine with a number of milliseconds loaded into the X register. After wasting 1 millisecond, we decrement the total remaining to waste. And then we loop back to start the small loop again until the X register also gets to 0. It's a loop of loops. And finally, when X gets to 0, we've wasted the correct number of milliseconds, and we return to whoever called us with an RTS instruction. And there you have it, a short, simple, and fairly accurate delay routine that can handle anything from a single millisecond all the way up to more than a minute. Not bad for a handful of bytes of memory. So let's give this a try by setting one LED pattern, delaying for a few seconds, and then setting a second pattern. Let's enter this program from the monitor and run it. set the program counter with Control-P, and then the G command with a breakpoint. I'll record the result so we can check the duration by counting the number of video frames. And that looks about right. DaVinci Resolve tells me the clip is exactly 5 seconds long. So we're within 1/24th of a second of 5 seconds. Not bad. In point of fact, when I first did this with my initial value, I was about 1/3 of a second too long. So I kept subtracting from that initial LDAB instruction until I nailed it with Hex 7.5. The difference between what I calculated and what worked in reality probably has to do with other instructions in the program that I didn't account for, and the fact that the robot's OS is still running an interrupt routine to scan the keyboard, check sensors, etc. For now, what we have is definitely accurate enough. There's one more LED-related thing we can try before moving on to solve the mystery of the hero's random speaking lights. Let's make a binary counting routine so we can watch the lights progress through all their possible values, from 00 to FF. For this one, we'll set up a loop using the A accumulator. Recall that I said A gets used a lot, so we use B instead for our delay routine? Well, this is exactly that situation. We'll be counting the A register from 00 to FF, displaying each step to the LEDs and delaying a much smaller amount of time using the delay routine. And now it's time to dig into some technical details of how the LED display works at the hardware level, so we can finally solve the mystery of the random lights. To start with, let's build a single LED circuit on a breadboard using the same wiring logic as the ones in the Hero Junior. We start with a single LED. Its schematic symbol is, and in real life it looks like this. LEDs use tiny amounts of electricity and convert it directly into light with very little waste. But they have a weakness. They cannot handle very much current flow at all. To limit the current flowing through an LED, each one needs a current-limiting resistor placed in series with it. For most LEDs, that's something around 220 or 330 ohms. Here's a 330 ohm resistor between the anode and the 5-volt power rail. So now we can connect the other side of the LED, the cathode, to ground, and the LED lights. Simple. But how could we turn this LED back off? Well, one option would be to disconnect the ground wire, like so. But in a computer logic circuit, that's not the normal option. What we need is to control the state of the LED by sending either a logic 0, ground, or a logic 1, 5 volts, to the cathode of the LED. So a logic 0 would be the ground connection we currently have, and a logic 1 would be moving the wire over to the same 5-volt rail that the other leg of the LED is attached to. In that position, both legs of the LED are at the same electrical potential, so no current flows and the LED turns off. So counterintuitively, the LEDs in the Hero Junior are wired in just this way, so that you turn them off by sending a logic 1 and turn them on with a logic 0. And this tiny fact helps to explain why the lights in the Hero Junior's phoneme playback do not look correct. Here's a high-level overview of the ICs involved in driving the LEDs in the Hero Junior. They receive their control signals from U215, Peripheral Interface Adapter number 2, its A port specifically, Those 8 pins directly feed the cathodes of the 8 LEDs on the keypad display. So to turn on a light, we set the matching port pin to 0, and to turn off a light, we set it to 1, exactly the opposite of what we'd expect. In fact, if we do a quick disassembly of the LED out routine using the I command in the monitor, we see this. See that COMA command? It takes the value we sent to the LED out routine and turns it into its logical complement, which means that for every 1 in the original value, we now have a 0, and for every 0, we now have a 1. It's this inverted binary number that is sent to the LEDs, showing us the value as we'd expect to see it. Essentially, we've negated the strange way the LEDs are controlled in hardware by inverting the number in software before we send it out. But how does that relate to the phonemes sent to the Votrax SC01 voice synthesizer chip? It's very simple and very much based on the hardware. Port A of U215, the second PIA chip, does not just go to the LEDs. It also goes in parallel to the SC01's input pins. It serves double duty, driving both devices. And thus, when the output of U215 is phoneme values for the SC01, they are simultaneously arriving at the LEDs and being displayed as well. And they are being visually inverted by the fact that the LEDs are pulled high to 5 volts and normally on unless they receive a logical 0. So what we're seeing is the complement of each of the phoneme values. Let's try a quick experiment to see if we're right. Let's modify the phrase data of the Hello World program to have nothing but the same repeated phoneme, the one represented by hex 00, the very short EH3 phoneme. By filling the entire phrase with the same phoneme, we'll be able to see it on the LEDs long enough to confirm what we're seeing. But wait, we're only seeing 6 LEDs lit. Why is that? Well, let's take a look at the full phoneme list for the SC01. They range in number from 00 to 3F. They don't use all 8 bits of a byte. There aren't 256 different phonemes, there are only 64 of them. The last 2 bits in the full U215 port A byte aren't used for phonemes. But I'm sure I've seen one of those 2 top LEDs light up on occasion while speaking. What are we missing? What we're missing is the fact that for each of the 64 phonemes the Votrax chip can produce, it can generate them in 4 different inflections, 4 different levels of pitch, if you will. And 2 bits is the exact number of bits we need to represent the values 00, 01, 10, and 11, or rather the decimal numbers 0 through 3. So an uninflected phoneme is one with a value between 00 and 3F, and any number in that range has its last 2 bits set to 0. How do we make an inflected phoneme? We set one or both of those top 2 bits. In other words, we take the regular phoneme number from the datasheet and add either a 64 or 128 decimal or both to the base number. In hex, we add either a 40 or 80 to the base phoneme value. So for the 00 EH3 phoneme, our 4 different versions are 00, 40, 80, and C0. Let's try the last one with both inflection bits set. We'll change all the bytes in the phrase data to C0, except for that last FF end marker, of course. And now we run Hello World again. And voila! All 8 bits are set during speech, which means we are seeing the lower 6 bits representing the complement of the binary number 000000, and the upper 2 bits are directly representing the actual 2 inflection bits. The seemingly random lights are so hard to read at face value because 6 of them are the complement of the phoneme value in the datasheet, and 2 of them are the inflection bits we weren't even aware of. But those 2 bits are not complemented. As to that final bit pattern we see after every speech output, it seems to be a byproduct of the ROM routine that shuts down the speech chip after it finishes speaking. It's always a C9 bit pattern, 11001001. Could it be related to this particular sound? Time may tell. For now, there we have it. We've mastered the fine art of the Hero Jr.'s other form of user output, its LED lights. Next week, we'll turn our attention to input and see how we can use the built-in keypad in various ways to get information from the robot's user. And we'll build a very useful little routine as our class project. Until then,
Would you like to be a tender too?
Join us next time as we continue our restoration of everyone's favorite 80s robot. And if you like this video, don't forget to
Like, subscribe, and ring the bell.